Okay, so today you get to learn finally, what is a derivative in calculus and why is it so stinking important? You're going to spend a good half the year on or more on derivatives. In fact, one of the jokes in most calculus classes is whenever you're in doubt, someone will usually yell, take the derivative, because that's pretty much all that people remember about calculus. So first let's talk about what a derivative is, okay? It is fancy talk for slope. Oops. Let me get my pen working here. Okay. A derivative is the slope of a curve. Now, the reason this is actually different than what you've done since, 8th grade is your whole life so far, the only thing you've had to find the slope of is a straight line. Am I right? Someone will give you a line and they'll say, hey, what's the slope? And then you just do rise over run. But now what I'm telling you is that with calculus and something called the derivative, you'll be able to take a curve, any kind of graph or parent function. For some reason, my mouse is really happy, and I'm sorry, guys. It keeps clicking on this random stuff, so sorry. But anyways, what's happening is you could take a graph similar to this, and I can say, what is the slope of this? And what the derivative does for you is it's going to enable you to go to any point on this graph and know what the slope is. So like, because hopefully you can tell that, the slope here is different than the slope here, different than the slope here, here. All of these have a different slope. And so, sorry gang, I can't stand the boxes anymore. So, in closing for something like this, just to kind of close out this box, what you're going to notice is instead of the slope just being one number or the derivative just being one number, now the derivative is going to actually be an equation. You're going to need an equation. Because slope is changing, okay? So that's what the derivative is. It's the slope equation. Hopefully that's not clear as mud. Hopefully that makes a little bit of sense. Okay, graphically relating a function to its derivative. This might actually help you out just a little bit. So the idea here is that if I have a function or a graph, let me draw something like this. Let me go back to just a funky, like, ooh, okay, something like that. So if I have a curve and what I'm trying to do here is talk about, well, what is the, derivative, or what is the slope? If I were to ask you what is the slope, you better ask me where, because the slope is different from point to point to point. And so what you need to be able to do is sort of zoom in on an area. So like if I said, okay, hey, I want the slope right here. Then what you're supposed to be doing is you're supposed to be able to zoom in, like I would imagine if we could zoom in on this box right here and sort of make this larger, so ignore all the rest of the curve. And if I zoomed in on this, it would look something like that, right? It has a little bit of curve to it still, but we might even zoom in a little bit closer on this point. So this is the zoom in, by the way. And the goal would be, well, what's the slope here? Well, see how this, once we zoom in, it looks straighter, it looks more linear than it did over here. Well, you get it to where it looks so much like a line that you can just do the rise over the run. And whatever that rise over run is, that's your slope at that point, or that's your derivative at that point. So you're going to get a derivative equation, and what it's going to do is once you zoom in and you find the slope, like right here, it's pretty flat slope, okay? And maybe I would call that a slope of 1/2, like up 1/2 or something like that if we had this scaled out. And so the derivative equation, what it's going to do is it's going to go to that same x value and it's going to say, okay, the slope there looks to be about 1/2, so it'll come up here on the y-axis to 1/2. and there'll be a point there on the graph. And if I did this at every single point, so like let's say I zoomed in right here, okay? If you zoom in with your eyes right here and you try to make this straight, the straight line might look something like that. Well, that's way steeper than that. So maybe that's like a slope of, I'm going to do that in black. I don't know. If that's 1/2, that would be like a slope of 4, which means on the derivative graph, we would go over to this x value, but then there would be a point up here, like if that's 1/2, then 4 would be up here. Okay. What about the slope right here? Well, if I zoomed in on this point right here, it would be the top of the hill, and at the top of the hill, it would be flat. So there'd be like this horizontal line right here. Well, what's the slope of a horizontal line? Well, it's 0. So at this x value, the slope graph would have a point at 0. And by the time you do this at a bunch of different spots, like we could do this all day long and then graph those green dots as we go, those green dots would form a picture, okay? And that's going to be the ultimate goal of calculus, is what's the equation that goes with all those green dots, and that's your slope equation, okay? And by the way, one last thing. When I've been drawing these little black baby lines, these are actually called tangents. You may remember that from geometry. If a line touches a graph in exactly one spot, it's called a tangent. So when somebody asks you to sketch a tangent line, that's pretty much what they're doing. They're just saying, hey, go look at the curve and try to zoom in with your eyeballs. Let's say you're right here. And if you had to draw a line that could only touch this in one place, you need to go to the outside of the curve and draw a tangent line. So it would look something like that. There you go. So what's the slope of that, by the way? Since we just did it, why not? Okay, what's the slope of that? That looks like it could be a -3 maybe. So this x value, we'd go down to -3, which would be about here. There we go. So, you know, my gut tells me if I were to keep doing this, you know, over and over and over, then our slope equation might look something like a parabola. Might look close to a parabola. So what you're going to learn through calculus is that it is in fact supposed to be a parabola, and it's kind of a cool thing. All right, so how does this relate to what you did last week? Well, guess what? When you did the limit definition of a derivative, if you look back at your answers, the first thing that you had was 2x, and you went through all of that algebra, right? The limit as h approaches 0, blah, 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 blah. After you did all that, your answer last week was 2. So what you just found was the slope of 2x, which you've known that since 8th grade. If I gave you that equation and said, what's the slope, you'd go, oh, it's just 2. So that's what you found. If you looked at the next one, what was it? I think I gave you like the square root of x plus 2 or something like that. Okay, so when you did all of that work that you did, and you got an answer of like 1/2 square root x plus 2. Okay, when you got that, this is the slope equation. And that is useful. Okay, it's actually very useful, because if you go through the limit definition of a derivative with all of the stuff from last week, and you get an answer, now if I were to say, okay, so what's the slope of f of x at x equals 1? So basically, here's your function, and I say, hey, what's the slope at 1? Well, the slope of the graph, you would just take 1, and you'd plug it in down here. You'd plug it into your slope equation. So hopefully that makes sense. If you want the slope, plug it into the slope equation. So 1 gets plugged in here, and you would math it out. So that would be 1/2 root 3. So this is the slope at the point 1 if you had the ability to zoom in really close with your eyeballs on that graph. Okay, so does every function have a derivative? Well, most functions do have a derivative, but it is possible to be non-differentiable usually at specific points. Okay, there are specific points or places where you are non-differentiable. So for example, if I had a graph that was like, let me do this. Alright, cool. So I know there's a lot going on there. Okay, I'm not going to ask you to like put an equation to this. I don't even think I could put an equation to that. But what I'm going to ask you is to look at this. You know, we've talked about continuity before, and you can tell when things are continuous or when they're not. We've talked about limits before. But what I want you to look at now is this idea of, is this differentiable? So in other words, is there a slope at every point? So if you look here, you can definitely think that there's a slope there because you can see all the points around it. So when somebody asks me, is it differentiable, I ask myself, can I draw a tangent line everywhere? And that's my question. Can I draw a tangent line everywhere? And if the answer is no, then you say where you can't draw the tangent line. So I'm going to go ahead and start a list because this is non-differentiable in specific places. Non-differentiable at x equals, and then we're just going to list them out. Okay, so first of all, anything in here is safe because I can totally sketch tangent lines. In fact, let me just sketch a few. That's a tangent, that's a tangent, I can sketch all these tangent lines. These are beautiful. Now, the asymptote is a huge problem though, right? Because I'm going to infinity and I'm going to negative infinity. There is no tangent line that I can draw at that spot. So whatever that x is, so let's say that that was 1, 2, 3, 4, 5, 6, 1, 2, 3. We'll do that. Okay. So when x is 3, we have a problem. It's not differentiable because I can't sketch a tangent there. Okay. Now there's two other places where you cannot sketch a tangent. One of them is going to be this funky, sharp, mountainy point here. Okay. This actually is called a cusp, but at a sharp turn, you can't draw a tangent, and the reason why is because if I put a dot on it and I'm like, oh, let me draw a tangent line, I may draw a tangent line like this, but you may have come up and said, no, I want the tangent line to look like this, and somebody else may have drawn it like that. There's a bunch of ways to draw the tangent, therefore there's no slope there. So at 1, 2, 3, 4, 5, that's a bad spot that is non-differentiable. And the other spot that's bad is the end point. So if something has an arrow, it's safe. So this is safe. But if it has an end point, this is not safe. So 1, 2, 3, negative 3 is a bad spot. And the reason that this one's bad is the same as this. How would you draw a tangent there? Somebody might do that, but somebody might do that, and somebody might do that. We could all draw a different tangent. And because of that, it's not differentiable. There is no existing slope or rate of change there. Okay? So I know this is very abstract, and whenever you're not here to draw with me and point at things with me, it's a little tougher to explain. Hopefully there was enough substance in here though that you can attempt the homework. Now the homework is going to ask you for things that I have not specifically done in this video, but they're things that you already know how to do, probably from like the previous week or weeks. So don't just give up on it. Try as much as you can, and worst case scenario, watch me do one of them on the solutions video, then try the rest on your own. Okay, but good luck to you guys. If you come to tutorials with me, I'll do a much better job, I hope, of trying to really get you to wrap your head around it. And I have an activity we can do in person as well. All right, we'll see you guys in a sec.